Last but not least, the I/O system based on 4.4 BSD. Alright, so Mac systems are running BSD, not quite 4.4, they're running a little bit different. Modified version of BSD. Actually, iPhone runs on BSD. And Android phones, BSD-ish. Not exactly BSD, but all mobile devices these days are running on mini microkernels that are created. I shouldn't say iPhone runs on BSD, it doesn't really. It's a modified version of the Apple OS, which runs on BSD. So iPhones and Mac OS X, similar, except for the iPhone software is definitely stripped out. It is not as feature-rich as the OS X, but it is a mini version of OXS. OXS runs on BSD. Similar BSD. Not 4.4. What do you need to know? BSD stands for Berkeley Systems, based on C. Most popular breed because it's very generic, and it's flexible and it's extendable. So properties of the I/O subsystem, and you're wondering, what in the world is an I/O subsystem? I/O is essentially the core of the system, and it makes it, and this is where it's interesting that I/O subs in this particular title of this lecture based on, and it's very specific in the title for a very good reason, because this varies significantly between different I/Os, so between different OSs, excuse me. Input, output, and I/O is like the core of the operating system. This is where another reason for why a lot of the Linux breeds differ. They vary. So what are some properties of I/O subsystems? Well, the unified interface to hardware devices, both for users to other parts of the kernel. The abstraction, so anonymizes. What does that mean? It makes it all the same. So as I was saying previously, and I've been saying all weekend, everything on Unix is treated like a file. It is, actually. That's how we make it anonymized. We don't care what it is, we all treat it the same. So if we make everything the same, make it all a file abstraction, have a file descriptor to it, then we're working with descriptors. It doesn't really matter what it is, commands are all the same, the processes work in a very similar fashion, and we can be consistent, and we don't have to learn as much. We don't have to know as much in terms of being functional. We also have buffer caching systems, general device driver code, and hardware-specific device drivers that go along with this. Four main kinds of I/O. We have files. Everyone always refers to I/O as the file system, or as input-output, C in, C out, printf, scanf. Actual files themselves, although this is too restrictive. We have file pipes, which are files. Because remember, everything on the Unix system is a file. So you'll walk home this weekend at least remembering one thing. Everything is in the abstraction of a file. Pipes are files. Actual hard drive files are files. Streams are files. Devices are files. We have hierarchical namespaces, locking, quotes, attribute management, protection. All of these are sort of characteristics that go along with the file system concept. In a Unix environment, we load the file system on as a separate module, and we can get support for FAT32, for extended, for NTFS, for different OS supported file systems. We just load it on, which makes it flexible. It's an external part. It's part of the I/O subsystem. The socket interface and networking requests are also considered part of the I/O system. So are block device interfaces. You're like, what is that? That's a device driver. Device file, I should say, is the block interface. Structured access to the device uses a buffered cache, minimizes I/O operations, synchronizes with the file system operations, and uses kernel I/O buffers. How many people have actually ever written a device driver before? If you've written a device driver, this makes a lot of sense, and you're like, oh yeah, I know about that stuff. When you write a device driver, you're looking at kernel-supported operations for opening, closing, starting, stopping, basic system call interface to well-known structures that are all related to I/O. And you're working with a file descriptor. First, you're creating a file descriptor. You're loading on code that says, read so many bytes into a buffer and store it here and call it the read. Write so many bytes to a buffer We call it the output or the write. Write to, and then you have a certain port information, a certain maybe an IRQ or something that's associated with the hardware interface to it, which is usually made by the manufacturer actually. It's all designed out for you, and pieces of the driver is actually written for you already because they have to, unless it's proprietary created hardware, they have to give you the interface to it. So usually you have a low-level supported interface to it that you base the device driver on. You build the driver, the kernel loads the driver, and now you can open and close the CD-ROM door. Now you can read and write to the USB disk. Now you can do all sorts of activity. It just provides the kernel level interface to the hardware, is what that device driver is doing. And most application developers don't write device drivers. You only write device drivers if you're an electrical engineer and you're building your own hardware, and your own hardware isn't going to have a device for it. Isn't going to have a driver available because it's brand new. It's something you created yourself. And then you normally have to ship that hardware with what they call device drivers. Everybody knows that from Windows because it says, hey, would you like to download the driver? And there's a driver for everything available on the Windows system. But Unix environments, you can load a microkernel on a piece of hardware you developed yourself. You don't have any drivers for anything. What do you need a driver for? Every single piece of hardware that's on that system. Maybe outside of the CPU. Actually, including the CPU. When you load and build a kernel for an embedded systems device, you're compiling the kernel to work with the CPU, with the I/O channels, the I/O features, with all of the supported hardware components, including the interfaces to all of the drivers. So that's kernel building. Basically, once you put the kernel on there, everything else works above the kernel, from what we've understood in Unix and Linux so far this weekend. And embedded systems actually is a really cool area to get into if you're interested. A lot of jobs in that area because everything's mobile these days. In fact, all those little tablet computers out there, you've got embedded Android builds where you build an Android kernel. It's based on Linux, the same concept. You can put UC Linux on those suckers. You can put anything you want on those suckers. There's small patterned, small builds of Linux. UC Linux, one I just mentioned a few minutes ago, is one of the original versions of it. It makes an extremely small kernel file. Well, you're thinking about an embedded system, you're not going to have a huge disk on that thing. You're going to have a little flash memory on that thing. Maybe, if you're lucky, 10 megabytes or something like that, 5 megabytes. You're not putting that much on there because the thing's so small. It's fitting inside of a watch or something. You're looking for a small memory footprint. You build a small little kernel, configure it with the hardware, put a UI on it, and voila, you've got a hardware device that works, that programs a microwave or something, or that does, all those would be considered embedded. They're embedded because there's no user interface that is graphical that comes from a terminal window. Instead, the interface is coming from a number pad or from an LCD screen or something like that nature. So, you think about how many coffee makers are out there, microwave ovens are out there. Most of your appliances have embedded programs that are burnt onto chips that are put into the hardware that run, and there's an operating system on everything. Everything on it, even a temperature controller for a room has got an operating system on it, and it's usually Unix-based, Linux-based. So that's why it's good to take a Linux class if you're going to get into embedded systems, because it's all based on that usually. It doesn't have to be. Now the biggest trend is Android. Android for embedded systems, which embedded Android is really powerful, actually, because it's more automated and easier to work with than Unix, the regular old Unix stuff. Okay, so reading a byte from a file causes a block to be fetched, and the block is stored in a disk buffer cache, and then the file I/O is actually initiated. So, because I went off on tangent, I'll just reiterate the point. The four main kinds of I/O: file system, socket interface, device driver interface. The last but not least is the character device interface. So, device driver interface and block device and character device interface are two of the different ones from other types of operating system environments you might be familiar with. Character is unstructured access to devices, where block is structured access. Block is normally, in fact, both of them are done in forms of driver implementations. And they both have pros and cons, and I'll go through that in a few minutes. There's two types of character device interfaces: actual character devices, terminals, LCDs, anything that takes output in the form of something that a human can read, it would be considered a terminal. And then we also have raw access to block devices such as disk drives, tapes, CD-ROMs, something that's read-writable. So I/O doesn't use the buffered cache. So in terms of the block device, we cache something with a file descriptor. We read and write to the file descriptor, which is nothing more than buffered memory, because we don't want to continuing to read and write to the hardware. As a general rule, in terms of speed of access, anything closest to the CPU is fast. Anything farther away from the CPU you get in this entire computing system, the slower the access is. And the thing is, everything that is farthest away are those resources or those devices. So your CD-ROM drive, your LCDs, your keyboards, your number pads, membranes, all that stuff, farthest away from the CPU, slowest access. So you're trying to bring it closer, so you buffer it in memory. And you read and write to the buffered memory, gives you faster access to the hardware because it's farther away, so you're not going as far, essentially. Plus it also allows you to accumulate commands and use resources that aren't necessarily on the hardware. This hardware does not have their own local memory, so you're using something that is going to facilitate some communication, make it run smoother. So I/O doesn't use the buffered cache, and requests are still in multiples of block sizes, and the requests might need to be aligned. They might need to actually be ordered. So internal I/O structures, device drivers, they are modules of code dedicated to handling I/O for particular pieces of kinds of hardware. So there's a couple of different philosophies. We had the unikernel, all in one. If you're working in an embedded device environment, you have a unikernel. There's another word for it, but it's a single kernel. Monokernel is actually referred to it. One single kernel runs everything. What is that? It's one program, one file that boots up, that starts everything, has the UI in it, has all the device drivers, has everything. Or, if you were installing Ubuntu on your computer, you're not installing a single kernel. You're installing, well, if you're actually installing it, not running from a live disk. And even if you are running from a live disk, you're getting what's called a micro. It's a micro, but it doesn't have anything in it. It's small, extremely small. Monokernels, one single kernel for the entire system is huge. Well, in comparison. But if you're working on a small embedded device, it's better to have one big file that's going to take up all of the file space than it is to separate it out among different files. If you have a microkernel, it's really small. It doesn't have anything in it. What does that mean? None of the device drivers, none of the modules, none of the support for I/O or anything is in that kernel. That means you can create one kernel loaded on every single computer out there. Every computer in this room can have that same kernel on it. And you just keep loading on software drivers and device drivers for every single piece of unique hardware that is added to each one of your individual computers. And then you have Windows, and you have the Mac OS X actually runs that way. You don't build a different, you don't have to because Macs are all the same. But if you go out and look at Windows Intel computers, I'm looking at 1, 2, 3, 4. You guys all have Dells. Are y'all from the same place? I'm looking at 4 different varieties from 4 different manufacturers out here. I guarantee it, your hardware components aren't even the same. In fact, I guarantee you 3 Dell people, actually 4. You 4 Dell people, because you 3 have Dells and you in the back have a Dell. Your build on your computer probably has miscellaneous parts that not even the manufacturer even knows is in there. Because they're built overseas in a manufacturing plant, and it's like this week we have I/O cards for the graphic adapter. Here they are. They come from nowhere. And your computers are piecemealed. I mean, they come from parts all over the world. Even the same among the same batch, there's probably differences between the sources of some of these components. Mac at least knows exactly what's on it, hopefully. I shouldn't say that to give other people credit. I'm sure they run into very similar situations. Everyone who does offshore manufacturing has the same problem. You don't know exactly what goes into that product, or where these pieces are coming from, or has it been tested? We don't know that either. Some companies do better testing on their end products and on their components and have higher grade products because they have higher grade components that are going into it. They're not generic. But let's say you're building an operating system for this piece of hardware. Let's just call it hardware X. You don't know exactly what's in the hardware X. You have some commonalities, and everything is IEEE certified, and everything's supposed to be compatible. But just as we noticed earlier today with one of the Dell systems here, none of them are all the same. You load a piece of software on it, not going to work the same. Not going to work identically, depending upon which Ethernet card you have in there. Which, in fact, sometimes it's the screen. It's this VGA or EVGA or whatever it is you're using as a graphics adapter. Not all has the same memory on it. In fact, some computer builds from the same lot have different amounts of memory. Depends on what's on that graphics card module that gets put into that system as to, oh, we had a sale on it this week. Here, oh, we ran out of the ones you really wanted. We substituted your order with these other cards. They have a gigabyte of memory on them. Wow, bonus, Or some of them even have different graphic cards in them completely from different manufacturers. The point I'm trying to make is you can't build a single kernel for these things. It's impossible because you don't know exactly what everybody has. However, you could ship a Windows kernel that is a microkernel that only has the basic necessities needed. You need an Intel chip, or you need a, Intel compatible chip in there. It can be AMD, it can be Intel. You need the processor to be consistent-ish. But Windows will actually load on this Intel processor on my MacBook, actually. I can strip off the Mac OS and load Windows on it. No problem. It's an Intel processor. That's basically all you need is an Intel processor. Everything else is loaded on top of the kernel in form of kernel modules. So if you can separate out the functionality into modules, drivers, aka modules, you can put them into separate files and have the kernel load them up. Then you've got a universal operating system that will work on practically any platform. Your Linux breeds are running that way. Same way. So if you installed Ubuntu, you have different drivers on there. As a person over there who installed on a different computer, person over there who installed on a different computer. All different depending upon what hardware you have. As a smart install should go out and look at your hardware. Say, oh, these are all the things you have. If you don't have a read-write drive on your system, CD-ROM drive or DVD that's read-writable, no need to have the module on there. Strip it out, take it off. So people who build their own kernels make the microkernel even smaller. Because think about it. What if you only have 2.0 USB, USB channels? You don't have full others. What if you only have support for a certain amount on your VGA card? And you only have certain I/O on here, and you're only running with SCSI, you don't have any IDE, anything on the system, right? Why have all that stuff loaded when your computer starts up? You don't need any of that stuff loaded. So you strip out all this extra stuff you don't need, make the kernel smaller. What happens? The computer runs faster because it's only loading what it needs. It knows exactly what it needs. And you can specialize it to optimize the use of what it actually has and make sure you include drivers for things that it actually has. So people who grow their own, build your own kernel, are doing it to optimize the functionality of their system because they can specialize the drivers, specialize the modules, delay loading on certain things. Just because you put it in the kernel doesn't mean you can't add it on later either. So some systems are adaptable by loading on special modules. You can't really remove something from the kernel after the kernel is built, but you can recompile the kernel, which is what most of the people do these days. So that explains item number 1, modules. So what I'm talking about is kernel loadable modules, or what this is referring to. So the code is dedicated to handling I/O for particular kinds of hardware. Any type of hardware, every hardware has a module, whether the module is compiled with the kernel or whether it's called a kernel loadable module. It's loaded by the kernel. Drivers define a set of operations via the well-known entry points, the read, the write. There are some common driver operations between all drivers. Obviously, there's an open, a close. Every hardware device needs to be open. It needs to be initialized. It needs to be closed when you're done with it. What do we do in hardware? We're generally, for I/O ports, we're reading and writing. What else do we do with the hardware? Read a CD-ROM, write a CD-ROM, or file. So block device interfaces is kept in what's called the BDEV, well, SW structure. Most of it, if you want to know what device drivers you have, go out to the DEV directory on your computer. If you have a Windows, excuse me, if you have a Linux or Unix box. The dev stands for device. Inside dev, you've got bins and you've got a bunch of other stuff. Not only do you have interface files, but you have the device drivers themselves, and you have all of the support that goes with it, all of the temporary files and stuff that you need to run that thing. Some of them are in character text form, and most of them are in compiled assembly language. Most device drivers are written in assembly language because they need to be loaded quickly. They need to be residing in memory constantly. You can't write that in Visual Basic and have that running all the time. It would take up way too much memory. They need to be efficient, and they need calls for low-level I/O. And you can't have a high-level system call and a high-level API. So you don't usually use APIs for device drivers. Instead, you use system calls. Character-to-device interface is kept in a CDEV SW structure. And it's nothing more than a configuration very similar to the device it's going to, it's to the block device that's going to give you the same capabilities. Here's the big picture. This is the kernel I/O structure. Here's the hardware at the bottom. The system call interface to the kernel is on the top. The system call interface interfaces with the drivers. The drivers are loaded by the kernel. Every single piece of I/O in that system has a driver for it. So we have two categories. We have the block device driver on this side over here, and we have the character device driver. The two forms right over here. A little bit of differences. The buffered cache with block device is buffered, a little bit heavier weight, a little bit more support for certain things. Cooked disks or disks, file systems, local naming systems, NFS file systems, Mac file systems, Windows file system support for everything you can possibly imagine ends up in the buffered cache category, which ends up having to be a block device. Block device means nothing more than the fact of having a cache associated with it, which ends up taking up extra resources. Why do you need a cache? Because you can't, when you open up a file on any operating system, you're not reading and writing to the block disk. Instead, you have a driver that opens up the block disk, finds all of the blocks that are associated with that file, creates what's called a file descriptor, puts it into memory. That's this buffered cache. Not only do you have buffered cache that works with the hardware, but you also have memory that's associated with the file descriptor and main memory. It's associating the blocks from the cache that might be associated with the hardware, if the hardware has cache, which sometimes most hardware devices that are using any type of file abstraction will have a cache. So your faster running CD-ROMs and your faster running DVDs have a local memory on them that's used as cache so that the I/O can be buffered from a hardware perspective and used in the driver implementation. What is that? It makes the reads and writes faster. So it's the same kind of spec you see on hard drives when you see disk seek times. And what is that? That's the motion, how long it takes the arm to get from one point of the disk to the other point of the disk, which is a hardware function that's controlled by a driver. So depending upon the driver implementation and the file system support that's loaded on that disk, speeds might vary depending upon what the utility of the file system, what it's doing. Certain file systems are faster than others because of journaling or because of indexing. If you've ever gone into the file manager, looked at the disk manager for Windows, you can see you can put on certain things to index, you can cache, you can optimize certain things. These are using memory that's associated with RAM, that's associated with the device itself, that's used as a caching system for the device drivers for the disk and for the operating system to speed up and to optimize the reading and the writing. So, and the concepts are pretty much the same among different operating systems. Unix uses journaling or indexing. Windows, I believe, what does Windows use? Indexing? I haven't looked at that feature in years, but if you go in and look at a drive and check out, there's usually on the bottom of the screen there's some options to turn this on or turn it off. And it's associated with how the files are stored, whether they're cached or not, or something like that. Sockets end up over here. Virtual machine. This is a virtual machine kind of concept. Your VMs are going to go down into this level here. Your network protocols are in here. Your network interfaces are in here. These would be all of the I/O subsystems that would be associated with it. A VM is actually an I/O subsystem because there's a filter from the underlying I/O that goes through the virtual machine that provides the abstraction for everything above it. And this is actually not a bad kind of concluding picture of the kernel environment, but this is only outlining the I/O systems. So imagine we have kernel processing systems, CPU scheduling systems, main memory management systems, process abstraction, process control blocks. A lot of stuff goes into the build of a kernel in an operating system. So device numbers. So how do we select the device driver and the actual device? In Unix and Linux, everything is numbered. So that's why you have HD0, HD1. In fact, you can't really see it on a, I don't know, can you see it on a Windows system? Does this ever see the hard drive? SDA1 SATA for SCSI device versus IDE devices. Yeah, or do you see, what was USB? Like sometimes it says USB 1, USB 2. Long story short, they're categorized. All devices are separated out into categories as to what it is. And HD is a hard drive. SDA is a SCSI hard drive. And the device numbers of the first drive usually starts with 0. Because Linux people or programmers, the road arrays start with 0. So counting numbers 0, 1, 2, 3. So if you count up all the devices, they're in different categories and everything has a number associated with it. So why is that? So that the kernel knows what device you're talking about. Keeps track of a device list in a vector. Associates drivers with each one of the devices if you wanted to. In fact, this is the case. You have an IDE or extended IDE drive connected, and you also have a SCSI drive connected. You're using two different drivers. Kernel knows that this is device over here. That's the device over there. When you look at this device, you use this driver. When you look at that one, you use that one. So kernel keeps it all organized. In tables, the device numbers, they major in a minor pair. And most systems use a numbering with characters, hence the HDA, along with the number. For device descriptions, along with numbering. So it makes it easier for people to go, oh, hard drive. Oh, that's the partition. It's usually partition-oriented as well. You can have one physical disk with HDA 0 through 10 on it, depending on how many partitions you've got designed on that. I believe Windows uses numbering systems exclusively. You know, C drive, D drive, F drive, G drive. If I put a CD-ROM drive in there, I'm going to get, you know, some sequence starting with D or something, or F or G or something. If I put it on a Linux system, I'm going to get, well, what kind of CD-ROM drive is it first? And is it a DVD or CD? And then I'm going to get a device number associated with that device. I'm going to go to my dev bin directory, and I'm going to see it right there. I'm going to see which one it is, or the bin or the dev directory, depending upon how your system is configured. So single devices have two major numbers, one each for the block and the character, because if you remember, we have two separate subsystems on the I/O on a Unix system. We have both a block and a character. Most people deal with the block device, which is going to be your drives, your devices. Character device is going to be for I/O to screens, monitors, LCDs, some networking adapters, terminals. Minor number selects which of the possible many devices are out there, which one it needs, and interpreted by the driver itself. Lo and behold, our device drivers. This is some generic information, obviously. This is not a substitute for a course in building device drivers. Nobody does this anymore, though, because there's a lot of drivers out there for everything. And manufacturers are really good now at providing support for hardware. In the old days, what do you mean PC operating system? What do you mean device driver? What do you need that for? You know, so okay, no problem. Now there's a little bit more support in the community, so you can get device drivers right from manufacturers who have programmers on staff who are writing them. So people will use their hardware, because if you don't use it, you don't do that. No one's going to buy your hardware. No one's going to buy your device if it doesn't work. If they have to actually put out an effort to make it work. In fact, you guys do that too as consumers. If you bought a network card, brought it home, plugged it in, and it didn't work, oh, you can return it, buy another one, it does work. So manufacturers do that too. So initialization probes device, sets initial software states, actually works with interrupts, creates handlers and things for certain events. Top half of it is the system call interface. May call sleep, to rest it, put it away until something else is running. The bottom half of the driver is the interrupt handlers. So no per process state or blocking. Instead, it handles interrupts in terms of what's going on between the device driver and the hardware. It has no idea anything about who's using it and why. It's not process oriented. There's no process associated with it. Error handling, that's the biggest thing. Crash dump routines, calls for systems when an unrecoverable error occurs. Usually it's timeouts and stuff. Because, in fact, that's kind of the way you can tell a really good driver from a bad one. How fast does it recognize that you put the disk in the wrong direction? Does it sit there? In the old days, things used to sit there for hours. Why is it not working? Now you do that, immediately the door just reopens. Oh, sorry, it's the wrong direction. So that's the advancements we've made in driver capabilities. I/O queuing, we're using with buffering and queuing. Move data, so how data is moved between the top and the bottom half of the kernel depends upon the I/O queuing scheme that's initiated. The top half receives the request from the user through the system call interface, records the request in the data structure, kernel keeps track of it, places the data structure in a queue, and we have I/O queues is where this comes out of, and each device has its own queue. Starts the device, if necessary, if the device is already initialized and already being used, it just waits, puts it in a queue and waits, and behind the current process that's actually using it. And the biggest part is those interrupt handlers, which is the way the kernel communicates with the hardware, so the device interrupts after completion of I/O operation. So most people think of interrupts as like, I don't know why, but most people think of interrupts as a bad thing. It's a form of communication. It's kind of like sign language. It's what the hardware uses to communicate with the kernel through the device driver. So it throws up interrupts, ones and zeros. It doesn't speak any programming language. It just knows electricity, no electricity. State changes, it's what essentially generates it. Removes requests from the device queue, processes as it communicates with cache memory that's associated with the device. Notifies the requester that the command has completed. How? Sends up a signal. So those interrupts, the kernel takes those interrupts and translates some of them into signals, just the same way as the user can create a signal. It's called a trap. It's a software level interrupt that's created in the form of a trap, which is similar to a signal. If you think about the concept, it's software that deals with events that goes on, or abstractions. Starts the next request from the queue if there's a next request in. Uses the queue to do its work. If the queue is empty, it dies. It sleeps. I shouldn't say it dies. It just sleeps. It goes to rest. It doesn't have to be initialized anymore. If you take an operating systems course that gets into the concept of CPU scheduling and I/O scheduling, you'll see some of the differences between the queues and the long-term, short-term, medium-sized queues that are used for I/O requests. Every I/O device has its own queue. The queue is associated with the buffer memory that the hardware interrupts are actually working with to say when it's done and when it's not done. And it's actually kind of all automated in an interesting sense. So top to bottom coordination between the top part of the driver and the bottom part of the driver, what makes it happen, what might happen if an interrupt occurs while a request was being in-queued in the top part. Well, the queue is just like any other shared data structure. So to enforce the synchronization, you use some routine that's going to synchronize and keep track of whatever interrupt occurred, put it into a temporary buffer, process the buffer once it's able to deal with it. So here's the interrupt mechanism to kind of give you the big picture. So the device interrupts, calls a glue routine through an interrupt table. The glue routine allows it to be machine independent because it's specific towards the hardware and the kernel environment. Glue routine saves the volatile register, saves the information it needs, updates the statistics, calls the interrupt register, whatever happens to be the controlling device for passing in the device number unit when it's ready, restores the registers, returns from the interrupt, keeps track of it. So we have the interrupt service routine. which is what ISR stands for, actually, interrupt service routine, which is nothing more than a process handler for the interrupts. So, and the glue routine is nothing more than the way of patching it together in terms of the interrupt dispatch table that is held by the kernel. Each one of the entries in the table interrupt vector has a glue routine, which is a driver process, a software application, something that is programmed to deal with these interrupts that happen. So block devices. It's a user abstraction, array of blocks. So we have physical devices. Those are those disk tapes, drives. And then we have driver that converts the byte-based requests into the blocked I/O. And the block I/O uses a buffer cache, as we've seen. And one can use a raw device to bypass the buffer cache, but coordination is actually kind of critical in terms of multiple synchronizations. The buffer cache, by definition, and the system caches blocks and returns the portion that's read. Think about small reads from a disk, actually, is a good comparison. Synchronously writes what can be done with a sync. So, system caches the writes periodically, flushes the dirty blocks to the disk, which are just blocks that have changed, end up being dirty blocks, and then flushes a single file. So, depending upon if the user has performed a save, it takes everything and goes through and cleans out the dirty blocks, fixes everything up, and writes it to the file. So, unless you write it to a file, you're not doing anything. So the way that I/O normally works is through an open and a close command, a read, a write. So the open prepares the device for I/O. The only thing an open does, seriously, is take the device, put it into an initialized state, so it's woken up, it's not asleep. Reads whatever it's supposed to read, puts it into a cached area, buffered cache, and then creates a pointer to that from memory. So it verifies the integrity of the medium, makes sure that the floppy disk is inserted in the right direction, that you've mounted the disk correctly, the file system is actually present. It's not the same as opening a file, although it uses the same interface. So opening a file is a little bit more. To open the device block is a little bit different than opening a file, but the concept is very similar in terms of what's going on. In terms of the interface, we have the strategy, which is a separate method or function for which you start to read-write operation return without waiting for it to complete. It would be the default to start the read-write. It can also synchronously can also work or be called synchronously, so the caller sleeps on the buffer pass-in. So we have a B-read and a B-write that maps through any of this. So if you look at the C++, C without the APIs for buffered I/O, you're looking at block device interface, because we have F reads, F writes, B reads, B writes, depending upon whether or not we're using character or block I/O. And then you can kind of see the system call interface that works directly with the drivers. So to kind of recap the concept of that system call interface, it really is an abstraction that works directly and closely with the kernel, because there's no higher level API that has to go through a filtering system to get down into those system calls. So the programs that you write using system calls run faster because you're speaking the same language as the kernel and you're writing directly to those devices. You're reading and writing and you're communicating directly to the device drivers. When you use a higher level language with an API that's built on top of the system calls, you have more layers to go through. So the message takes longer to get to the kernel, long story short. It does get there eventually, but it does take longer. So most device drivers are written in lower level, and most modules and most interfaces from the user mode are written in low-level system call interfaces because they run faster and you have more access to the hardware and more hardware features available to you than if you actually used a higher level API. But obviously everyone knows the APIs are easier to work with, much easier to program than a higher level language that uses a higher level API. So block device interface, the close is called when the final client is using the terminal, the device terminates, everything's over with, then the device is going to close. It just closes all files or pointers, I should say, and makes the device available to be opened again. So device-dependent behavior. Disks don't really do anything. Tapes might have an end-of-tape marker, a rewind functionality that might exist on an old cassette tape or something. CD-ROM drives usually open up and spit a disk out or something. If you did a low-level system call close command on a CD-ROM drive, it's going to spit the disk out. The dump method is used to save the contents of the physical memory to the backing store. Okay, it's just like main memory concept in terms of the backing store is sort of like a swap drive-ish concept of main memory, where you swap things in and out because you don't have enough room in main memory, so you have this temporary storage area called a backing store. Instead of writing it back out to the disk, you go to an intermediate point and cache it temporarily because you might use it again. It's cheaper time-wise to pull it from the backing store than it is to load it fresh from a file again. So, a dump is used to analyze the crash. In fact, there's dump utilities in Unix that's used all the time to see what happened with this core dump. Take a look at it and see what happened. All disks must support this. This is what ends up in the lost plus found on the file system. You know your device drivers aren't working properly when you have a ton of files. In fact, you can test this on your MacBook actually. When you have repeatedly put something in the wrong direction, or you have repeatedly loaded on devices that aren't recognized, or you have repeatedly crashed something on your system, you have huge files in here. So a lot of these optimization programs go in and dump this out. Why? Because you get extra stuff stored you don't need. It takes up hard disk space eventually. Depending upon how many times you crash something, it just keeps filling up that directory, It's core dumps that ends up in there. So psize is a great function used to return the size of the partition in terms of the blocks. So this would be a low-level driver interface that would say, hey, how does the operating system know how big your hard drive is? Loads of psize. Says your partitions, and p signs for partition, your partition size is 1024. Ooh, okay. And so then it knows to take that as an abstraction. The driver takes that and translates it into block sizes that are associated with the file system support that you have to tell you how many files you can store on there and what files are stored on there, and gives you all the information associated with storage of that disk. So it returns the size of partition in terms of the block size of the blocks. You can actually change the size of the blocks on the disk. It doesn't help you to change them arbitrarily. How this gets changed is when you format the disk. So when you format the disk for NTFS or FAT32 or FAT12 or something, they all have different block sizes. So it takes and it creates a block size abstraction from the physical media and creates the fat allocation table and all of the other information that's associated with the format of that disk. So the operating system knows what it's got when it takes a look at it. Because it's generic disk. You can load anything you want on it. So how you format it is determined about how it's going to be used. Interesting thing about Linux is that it can read all of these formats. You just load on a module for it. So a lot of people like to use Linux and Unix because it's extendable. You can't really load. You can actually, this was a problem in the beginning of the iPods. We had a bunch of Windows peoples who don't have MacBooks who are buying an iPod or an iPhone. And the first couple of versions actually had this problem, and I believe it's still the case. They took it and they formatted it on, actually it came shipped with a Mac OS X formatted disk. Because when you plug the iPhone into your computer, iTunes, when it first came out, it syncs up with iTunes, and it's getting loaded on as a device. It's a disk, and it's being accessed. So, MacBooks understand the Mac operating system, but Unix systems understand it. But Windows does not understand Mac, and that is still the case. Because I have this problem all the time when I take USB drives that are on my MacBook and I go over my Windows system and it says, I don't understand you at all. I can't load it. So we had a ton of Windows people who ended up, and then they decided, oh no, let's just change it around. Now, when you open up a box on a new iPhone or a new iPod, it's FAT32 or NTFS, depending upon the model that you get, formatted. No longer formatted for the Mac, because most of the people that are using them are Windows people. They plug it in, they've installed all this stuff, they've downloaded stuff, they plug it in, and iTunes says, oh, we need to reformat this thing. And you lose everything that's on it. Just because you hooked it up into iTunes. All of a sudden you got to reformat it because it doesn't understand the disk. But it's the opposite. So you can take a Windows 32 disk and load it on the MacBook just fine. It reads it and understands it. It's a Linux-based BSD system. You can load it on any Linux box, Unix box, just fine. You just can't go the opposite way around. So it was actually kind of shocking. I guess they never thought, I mean, people who buy iPhones are not going to go out and buy MacBooks. You know, they're Windows users who are buying those iPhones and stuff, so they're going to load it on a Windows box. And so it's kind of interesting that they started out going, oh yeah, I just format it for the Mac. And then they discovered, oh, this is a problem for a lot of people, so switch it around. So much your iPod, actually most of your iPods aren't formatted. Some of them aren't even formatted anymore because why pick? So actually what I like to do is I take all of my USB drives, I go over to my Windows system and format them for Windows, and I use them on the Mac. That way I can give it to anybody. Although I'm using it on my Mac, I can still give it to Windows peoples. I mean, they're just fine. Because it's not formatted just for my system, it's formatted for everybody's system if I use FAT32. The other way around doesn't work. And it's not no fault of the Mac, it's just that other operating systems don't support it. So, and that's one of the beauties of Unix and Unix is that it does support multiple different file systems from different vendors and things. You just add the module on. So the size, the partition size makes sense mostly for disks during a bootstrap. You know, to calculate the location, information, determine the size of the swap drive, stuff like that. So disk scheduling or disksort, that's actually a low-level system call that you can run, implements a variant of the elevator algorithm. Which one is this? Well, elevators. If you think of the concept of disk scheduling and all of the different routines that you could possibly have for reading a disk, what wears out on a hard drive? The ARM. So what do disk manufacturers try to do? You know, they make the ARM as, strong as possible. But it's kind of like any mechanical device. The more you use it, the more it's going to break. And what does an elevator do? It goes to one floor to another. Usually, elevators go up or down. You get to the elevator door, and are we going up or down? And you press the appropriate button. Because you got one elevator that starts at the bottom, and it's an up elevator, and it goes all the way up to the top. And then someone presses the button, and then it goes all the way down to the bottom. So one of the ways that operating systems are designed to essentially make use of the hardware of a hard drive that has a mechanical arm is to have smooth movements. So the arm goes from one start of the disk to the end of the disk, picking up all the blocks it's looking for, and then it goes all the way to the end and it turns around and comes back this direction just like an elevator does. So you get smooth movements. In the old days, it used to do this. Didn't go from one end of the disk to the other. It goes like this, and you hear chunk, 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 chunk. After about, I don't know, 6 months, your computer goes chunk, 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 chunk. Oh, that's just the hard drive. And then the noise gets louder and louder and louder. And then eventually it stops completely. And you end up taking it over and putting a new hard drive in it. Because that chunk, chunk, your hard drive should not be making any noise, by the way. If you have a loud, mechanical ARM, old-fashioned, everything's solid. Everything from 2012 forward is going to be solid state. Because now we don't have hard drives that wear out. Solid state does not use a mechanical ARM. It doesn't run with the disk concept. With the disk plate concept, there's no ARM to wear out. Which means we can increase the efficiency of the disk access by optimizing the algorithm so that we can go chomp, 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 chomp all over the disk without using an elevator system. Because we don't have to worry about wearing the ARM out. So like Windows 95, Windows ME, chunk, 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 chunk all over the place. Windows 7, elevator. Smooth, up and down, like a ballerina. It's just easier on the disk. The more you move that arm around, the more you're going to wear out the disk. So the disk lasts longer anyway now, so because they don't make as much noise. Plus also, to give the credit, it doesn't really matter what algorithm you use, it's mechanical. Anything mechanical is going to wear out. So if you're going to shopping for a new computer, go solid state. Don't go mechanical drive, because you're going to need to go solid state eventually anyway. Solid state, no mechanical parts and pieces. Instead, it uses, well, that has their pros and cons too. You can only write so many times to a solid state drive before that wears out. It gets confused because it's leaving an imprint. In solid states have that problem to compare this with. You remember those carbon sheets? Some people still have them in checkbooks, but now they put one carbon sheet underneath each check. So when you write a check, it leaves a carbon copy on the check underneath. That's solid state. And in the old days, you used to have one sheet of that carbon paper, and they put it under, and you move the sheet for each one of the checks. If you're familiar with that, that's how they did it in the States. They don't do that anymore. Because after about 5 checks, it doesn't work anymore. Well, it leaves holes. Like, you know, not only does it make holes in the fabric or in the carbon, but you know, parts of it are darker than other parts. It's kind of like a typewriter in the old days. You had a typewriter ribbon. The more times you use the ribbon, eventually you replace the ribbon. Unfortunately, that's the issue with solid state drives. They're better if you write once and you just read from it forever. Because it's less wear and tear. The more times you reformat that, the more times you write to it, read to it, write to it, read to it, write to it. It's like a carbon copy. It's the same kind of phenomenon. But pros and cons, you know. I mean, nothing's perfect yet. They say nanotechnology for drives is going to be like the solution to everything. No mechanical parts, no carbon copy issues, nothing. All right, but that is not everything you need to know about the differences between these different drives. There's a lot of other factors that make differences in the terms of how long the media actually holds up. But disk scheduling, the qsort implements a variant. The sort itself is going to be implementing a variant of the elevator algorithm, and not every operating system uses an elevator algorithm either. What I was trying to give you was a background on the algorithm. Keeps 2 sorted lists of requests, and not to say that. Okay, going back to another comment, another disclaimer, not to say that the elevator algorithm is the best one out there. It isn't, actually. There's other disk scheduling algorithms that are better, actually. Okay. Keeps 2 sorted lists of requests, the current one, the one that we're servicing, and the other ones for the opposite direction. You know, it's kind of like when you press the button on the elevator. It knows, although it's not on your floor yet, that it's going to stop on your floor eventually, on its way down. So, switch whenever you hit the other end, you switch it, you go back to the other direction. So, modern disk controllers will allow multiple outstanding requests and will sort the requests themselves, actually. Disk labels, we all know about that. C's, D's, E's. Nobody actually puts a name on disks anymore. In the old days, everybody used to do that. You know, Barb's hard drive. My file. Some people do that. Actually, manufacturers do that on thumb drives. You load it up, it says Kensington. Because you're not going to change the name. So they should just put that on there because it's going to be on there forever. It's like, who changes their router name? You know, how many times you go to a building and you turn on your computer and it says, you know, Nexus, or it says, you know, it says some Cisco, or it's, you know, it's the same thing that Kensington does with their thumb drives. Yes, you're not going to change it. It's just an identifier name as part of the driver interface that gives again, another piece of information to sort the device. So the geometry of the disk itself is the number of cylinders, the tracks, the sectors of the disk, and the size of the sectors. The disk can have different geometries imposed from a low-level format. Disk labels are written in well-known locations on the disk and contain the geometry as well as the information about the partition usage. How much is available, how much isn't. It's constantly updated in terms of what you have going on, which is why, as a classic example, in the old days when people used to take these 300 gigabyte drives and they stick them in fact, this is still the case. Where's my 300 gigabytes of memory that I have on my 300 gigabyte drive? How come I only have, I don't know how much, I think it's like 40 gigs are taken away from you automatically. Well, you got to store this stuff somewhere. Where are you going to put the disk label? Where are you going to put the operating system support for this drive? So you lose drive space. You don't really have 300 gigabytes of that drive available to you. You have a percentage of that. We also have this concept called the bootstrap that comes from Unix. The first level Bootstrap loader reads a few of the disks and it finds the geometry of the disk. The second level Bootstrap routine, if it exists, like a grub menu. If you've installed Ubuntu, you've looked at grub probably, which is probably the most popular boot menu. It's secondary, actually. It comes from the disk. So it comes up and says, well, how many on this particular disk that we've read, and we're bootstrapping now, and bootstrapping nothing more than taking the boot and loading it up into the kernel is where that terminology is referring to. Grab's a nice menu because they say, oh, well, we have 5 partitions. We've got Linux, Windows, Ubuntu, all this stuff on this disk. Wow, which partition do you want? So grub menus only allow you to pick between partitions. See this link down here if you want to load up a nice dual boot system. So character devices. And that was everything you ever wanted to know about buffered devices. Character. Most peripherals except networks have character interfaces. You can actually have a driver, you can actually have both buffered device and character device all in one on the same hardware device. Not all in one, there's 2 separate abstractions, but you can have both simultaneously. For many devices, this is just a byte stream. So an LPT port for printing, a scanner port, some networking, but not all networking is done this way. In fact, most modern networking is not done this way. Terminal interfaces, streams. What are they? For the block device, the character interface is called the raw interface. So for block character, it's just, there's no buffer. It's just raw characters. Direct access to the device, you're reading and writing exactly. If you have an LPT, if you have an LCD screen hooked up to an LPT port, you're running with a character device driver, character styled one. Because when you say put a C on the screen, it goes through the device driver and actually puts the C, and there's no buffer, puts the C on the screen. And there's put an H on the screen, and it goes out and puts the H on the screen. And you're reading block to block on a LCD display. It says open, close, or done. You know, you ever go to a microwave oven and you see LCD screens, or you go to a coffee maker, you see LCD screens. This is how the information is getting to the screen, is through the device driver, which is a character device driver. And it's real-time activity. If you had to sit there and wait for the screen to update through a buffer, not very efficient. Plus, what do we need a buffer for? We only have 5 spaces on that LCD that we could possibly fill up. What do we have to queue up to put in there? We don't really have that much. So we could create a buffered information, but it's still sent without being buffered to the device. Faster, more real-time, better interaction, and we don't need anything else. It makes it run more efficiently, takes up less memory, fewer memory requirements. Streamline it. Must manage its own buffers, doesn't use a buffer cache, so you could actually set up a buffer, queue information, so and you usually see scrolling stuff at that point, and that's buffered by some device outside of the character device. Not a byte stream model. They'll have to talk in terms of understanding the underlying device. So there's size alignment. So usually you have pixel size that's defined with perhaps a spot. And it's usually, actually a lot of these LCDs work with arrays. You have index value for character 1, 2, 3, 4, or 0, 1, 2, 3, 4. And you just say, put this here, put this here, put this here. And then clear it all out. Put this here, and which is how those LCDs are working. It should only be used for programs that have an intimate knowledge of the underlying device, obviously, and the format of the device. How are you going to know how the device is structured? Otherwise, the chaos may ensure. You can't use nobody uses an LCD screen for, a desktop system. I'm talking about those little itsy-bitsy little, they're like little modules. You solder cables onto them, and they hook up to the I/O ports on the hardware. And it's usually used in embedded devices, and you write little programs that put stuff out there. It's usually status stuff like done, or press start, or to guide the user. It usually works with a membrane or something for the input, so it's input-output for small devices. Or a watch. A watch has one too. Digital watches have LCDs. Itsy-bitsy little components. Sometimes they're black and white. Usually they're green and yellow, black and white. Very small color components to them. They're not heavy graphic user interfaces. So here's some characteristics about the interface to the, because we have to think about the memory, the interface, the device, driver components. In terms of the interface, we open, close, just what you think, read, write, and do something. The Swiss Army knife call, highly dependent on the device, the local character, local control of the device. In terms of resetting, initializing device states, so you can kind of read through that on your own probably. This is where I'm going to actually stop, so some people just walked out. They just missed the end by seconds, actually. So I'm not going to go through this whole thing, but the concept of the file descriptor is what we get in terms of how all the devices are identified by the kernel. We come up with this file descriptor. Think of it more like a pointer. It's a pointer. We have a memory location. We have a pointer to the memory location that identifies the device that's loaded by the kernel. Think about it. If the kernel is loading up all this stuff that it doesn't know about, that has been given to it as modules to load as it booted up, where's it going to stick it? Memory. You're going to read and write to the memory? No, you're just going to get the memory address. Return the memory address, give it to the user. It's a pointer, call it a file descriptor. And there you go, that's how all the devices work, how everything works in Unix is through a file descriptor. So system calls use the file descriptors to refer to the open files and the devices. Read and write to that LCD monitor, that screen or whatever, through the file descriptor, everything universal. File entry contains file type and a pointer to the underlying objects. So socket, IPC, vnode, virtual memory, any type of object that might exist. So the user process looks at the file descriptor table looks up and finds out where it is, the file entry is in the kernel list, and then it performs whatever process it needs to do, depending upon what file descriptor it is and what the file descriptor is pointing to. And then the kernel kind of translates that from its kernel list, from its file entry list, and says, oh, this is a thumb drive, or this is an LCD, this is a membrane or something. So, and all devices are loaded this way. So we have a file descriptor. In fact, if you've ever done any low-level C programming with opening and closing files, actually even the higher level APIs use a file descriptor. And it usually comes back with a number. And that's the number the kernel has registered for your device. Actually, from the higher level APIs, it's usually 0 or 1 or something. Actually, you never see the number. It's kind of like pointers in C. You never really see the memory addresses of a pointer. But, it is a memory address. But who cares? You can't check for certain memory addresses. It doesn't know exactly what memory address it comes back with, so it's treated the same way. Alright, so what I'm going to do, because this lecture set is about 80 slides long, I'm going to take a brief tour through what it is you probably would want to know about, would be familiar with, and cover anything I see that's going to be good, that's going to be relevant. Opening file entries, yeah, reading and writing, object-oriented data structure. Everyone has opened files before. Each operating system and each Linux build is going to have and each file system is going to have its own opening procedure. And this is the file system support that is offering you the opportunity to open a file and to read a file. File descriptor flags are set. Again, these are implemented in the APIs. The flags, obviously, the ones that you're familiar with, are protection-oriented, reading, writing, read-write mode. When you open up a file from a low-level open, you're going to open it for reading, for writing, or for both. It's kind of like in terms of the descriptor flags, that's pretty much all you have to work with. There's other ones as well, end-of-file flags, syncing flags, interrupt-related or signal-related information that can be flagged. File entry structure counts, reference counts, message counts. These are all having to deal with some of the utilities and tools that you can work with in terms of the file system. When you run an FSCK to check the file system on the disk, you're looking at reference counts, you're looking at pointer counts and all sorts of different information that was accumulated by the inodes that says, hey, we're out of sync, or we're in sync, or something's been opened but it's dirty, hasn't been written, or something was never written, or So counting the number of times a process points to a particular file structure. You might have more pointers than you actually have registered. Any syncs is going to cause any syncs that differ in terms of what the count's supposed to be and what the actual count is are going to be anomalies. Those anomalies are going to end up as lost clusters. Or they're going to end up as problems that need to be fixed eventually, or they go away when you turn the computer off. Hopefully they don't give you any corruption in terms of the file system. But the counts are there just for error checking and for diagnosis as well as functionality. So they serve multiple purposes, but we do have structure counts. File structure manipulation that can happen, duplicating a descriptor, working with executing stuff. All sorts of different things can happen from a file manipulation point of view. The library that works with that is the file system or file count control that's going to be over the file system itself. And very few people mess around with this because why? Unless you're writing a device driver and testing it, looking at it, and loading one in, you might be using some of the flags, setting some of the flags. So, setting an append flag, setting a sync flag, setting or getting a process ID or a process group ID that's associated with it to send in the two signals or something of that nature to communicate with. Well, what process are you? What kind of communication methods? There's a such thing as a file descriptor locking, making it so it's not available. Early Unix systems didn't have file locks, so it used an atomic operation on the file system to simulate one. I'm not going to go into how, but there's downsides to that point. So locks themselves are now put into place. A file system lock or descriptor lock would say, hey, the file is already opened. Windows uses a locking system on the file system. If you open up a Microsoft Word file and you're editing it and you try to open it up again, it'll say, hey, this is already open. I can open it up in read mode for you. Unless you're using Google Docs, you're not going to be sharing files among different users on a Windows system. You could essentially open it up for non-locking, depending upon the breed of Linux that you have actually, and edit the file by using sort of a Google Docs kind of approach without the support for it. It's going to end up with some corruption in the end, especially when two people make different modifications and counterbalance what they're doing. Depending on who saves first, that's the file that you're going to get. There's no merging of information or anything like that. There is in Google Docs. So. Alright, so file description locking, locking the whole file, locking part of the file. You can get into the gritty details about how file locking works. You don't have to know that. For the purposes of this course, you don't actually have to know anything. From about slide number 27 forward, if you're studying this at home, so 1 through 27 is the testable material that you're going to be looking at, but none of this other stuff, I'm actually just going to skip through it right now. None of this other stuff is relevant to you, although it might actually be interesting. Virtual file system interfaces, different types of file system implementations might be of interest to you. It's a little bit more detailed than you're needing to know at this point, so I'm going to skip through it because, it is interesting information. However, you can download the slide set and go take a look at it. So, oops. Okay, there we go. Get rid of that lecture. That was as far as I was going to make it through that lecture. We have, that was lecture number 9. On lecture number 10 is optional. And I'm bringing this up just to show you, this is the last lecture of the course, actually. I'm not going to go over it this time. Sometimes I do go over it, depends on the term. I'll save you it for this one. It gets into the concept of file systems and distributed file systems. Primarily focuses on the complexity of the distributed file system. And as an example, most Unix systems work in a distributed manner where we have 5 Unix boxes and we have files for 200 users and they're stored on different boxes. And we're using distributed computing among the 3 different boxes to house up the information stored for the user, for each one of the users, for each one of those 200 users. So this particular lecture goes into the differences, and Windows 2000 doesn't even exist anymore. So it goes into the underlying NTFS, which is where Windows actually, the 2000 version was when we had the networking file system. NT file system actually came out. It is still supported, however, in XP and also in 7, which is good. But that's the distributed file system that's used as a comparison against the Unix distributed file system in this particular lecture. It's everything you ever wanted to know about NTFS and BSD distributed systems, along with all of the different problems that are associated with it, and a lot of different ways of getting around those problems in terms of you know, all of the different issues. So that is another optional lecture that you can take a look at. I'm not going to cover it for this particular section. But what I am going to do is stop this video and start a new one to recap the weekend section with all of the vital information that ITU students need to know.